Hello and good morning friends, welcome to CEC-UGC live lecture. Dear friends, as you know that we are carrying series on artificial intelligence, and this is the last lecture on artificial intelligence. Yesterday we talked about natural language processing, and today there is something very interesting for you. You must have heard about the robots. Now the question arises, what is the architecture of the robots, how robots are created, as well as in this particular lecture we would be telling you the history of the robots as well as the various types of robots. We also would be covering about the application of the robots. Thus this session is all about the robotics, and for this we have again with us in our studios Dr. Uma Shankar Pandey. He is an associate professor in School of Open Learning, Department of Computer Sciences, University of Delhi. I would like to tell you that Dr. Pandey has almost 25 years of teaching experience, as well as he has authored 2 books. One is on cloud computing, whereas the other is on e-commerce and mobile commerce technology. So, first of all, I would like to welcome our guest, Dr. U.S. Pandey. So, taking advantage from his immense experience, I hope that all those who are interested in robotics or all those who have heard about the robotics, this session is going to be very, very interesting for them. So, welcoming once again Dr. Pandey. Dr. Pandey, welcome to the EduSet lecture. As we are carrying a series on artificial intelligence, and yesterday we talked about natural language processing. Today robotics. Why robotics is included in the area of artificial intelligence?
See, in the development of the robotics, basically artificial intelligence uses tool. So that's why we are going to discuss about the history and including all different kind of architecture about this artificial intelligence, which is going to be used as a tool to develop the robots. Now let us start a brief history of the robotics. The mechanical automata in ancient Greece and Egypt, water powered for ceremonies. In 14th to 19th century in Europe, clockwork driven for entertainment. In motor driven robotics, in 1928, the first motor driven automata. In 1961, Unimate, the first industrial robot. In 1967, Seke, the autonomous mobile research robot. In 1969, instant forearm, dexterous electric motor driven robot arm. You can see the robot manipulators, mobile robots. These are basically machines which is governed by the programs and the control by the instructions which have been fit into this. Walking robots, you can see here humanoid robots. These robots have been made just using the different particles and articles in that way, and it had been fitted with the programs and the instructions. Autonomous robots. The control of autonomous robots involves a number of subtasks: undertaking, understanding and modeling of the mechanism, kinematics, dynamics and odometry, reliable control of actuators, closed loop control, generation of task specific motions, that is path planning. Autonomous robots, the integration of sensors, selection and interfacing of various types of sensors, copying with noise and uncertainty, filtering of sensors, noise and actuator uncertainty, creation of flexible control policies. Control has to deal with the new situations. Traditional industrial robots. Traditional industrial robot control uses robot arms and largely pre-computed motions, programmable using teach box, repetitive tasks, high speed, few sensing operations, high precision movements, pre-planned trajectories and task policies. No interaction with the humans. Problems. Traditional programming techniques for the industrial robots lack key capabilities necessary in intelligent environment. Only limited online sensing, no incorporation of uncertainty, no interaction with humans, reliance on perfect task information, complete reprogramming for new task. Requirements for robots in intelligent environments. Autonomy. Robots have to be capable of achieving task objectives without human input. Robots have to be able to make and execute their own decisions based on sensors information. Requirements for robot in intelligent environments. Intuitive human-robot interface. Use of robots in smart homes cannot require extensive user training. Commands to robots should be natural for inhabitants. Adoption. Robots have to be able to adjust to changes in the environment. You can see here the robots for intelligent environment, service robots, security guard, delivery, cleaning, mowing, assistance robot, mobility, service for elderly and people with disability. As maybe you are knowing, now different kind of robots are available for this service purpose. Even you can use this robot in a door just to see who is coming to your house, and he will easily try to understand which kind of person is going to be there. He will inform you accordingly. In the same way, for the security purpose also, a robot can be used now very easily. So, for this purpose you need not to have any special kind of training. These robots are already trained regarding the security and on. Same way, in the cleaning and other objects, these robots are being used for cleaning the sophisticated type of equipments. Otherwise also, these robots are so trained that they can assist you in different parts. Autonomous robot control. To control robots to perform tasks autonomously, a number of tasks have to be addressed. Modeling of robot mechanism, kinematics, dynamics, robot sensor selection, active and passive proximity sensors, low level controls of actuators, closed loop control, control architectures, traditional planning architectures, behavior based control architectures, hybrid architectures. Modeling the robot mechanism. Forward kinematics describes how the robot joint angle configurations translate to locations in the world. You can see here in the pictures the dimensions, how the arms have been fixed up. Inverse kinematics computes the joint angle configuration necessary to reach a particular point in space. Jacobians calculate how the speed and configuration of a actuators translate into velocity of the robot. Mobile robot odometry. In mobile robots, the same configurations in terms of joint angles does not identify a unique location. To keep track of robot, it is necessary to incrementally update the location. This process is called odometry or dead reckoning. Here you can see the mathematical equation, a differential drive robot, and how these equations will take place. Actuator control. To get a particular robot actuator to a particular location, it is important to apply the correct amount of force or torque to it. Requires knowledge of the dynamics of the robot, mass, inertia, friction. For simplistic mobile robot, F is equal to ma plus Vv. Frequently, actuators are treated as if they were independent, such that as if moving one joint would not affect any of the other joints. The most common control approach is PD control, proportional and differential control. For the simplistic mobile robot moving in the x direction, as we have mentioned, F Kp based on x desired minus x actual plus Kd V desired minus V actual. Robot navigation. Path planning addressed to the task of computing a trajectory for the robot such that it reaches the desired goal without colliding with the obstacles. Optimal paths are hard to compute, in particular for robots that cannot move in arbitrary directions, such that non-holonomic robots. Shortest distance path can be dangerous since they always graze obstacles. Paths for robot arms have to be taken into account the entire robot, not only the end effector. Sensor driven robot control. To accurately achieve a task in an intelligent environment, a robot has to be able to react dynamically to changes on its surroundings. Robots need sensor to perceive the environment. Most robots use a set of different sensors. Different sensors serve different purposes. Information from sensors has to be integrated into the control of robots. Robot sensors. Internal sensors to measure the robot configuration. Encoders measure the rotation angle of a joint. Here you can see how the output and waveforms are coming in that. Limit switches detect when the joint has reached the limit. Robot sensor. Proximity sensors are used to measure the distance or location of objects in the environment. This can then be used to determine the location of the robot. Infrared sensors determine the distance to an object by measuring the amount of infrared light an object reflects back to robot. Ultrasonic sensors, sonars, measure the time that an ultrasonic signal takes until it returns to the robot. Laser range finders determine the distance, measuring either the time it takes for a laser beam to be reflected back to the robot, or by measuring where the laser hits the object. You can see here the different sensors and robot sensors. Computer vision provides robots with the capability to passively observe the environment. Stereo vision system provide complete location information using triangularization. However, computer vision is very complex. Correspondence problem makes stereo vision even more difficult. Uncertainty in robot system. Robot system in intelligent environments have to deal with the sensor noise and uncertainty. Sensor uncertainty. Sensors readings are imprecise and unreliable. Non-observability. Various aspects of the environment cannot be observed. The environment is initially unknown. Action uncertainty. Action can fail. Actions have non-deterministic outcomes. Probabilistic robot localization. Explicit reasoning about uncertainty using Bayes filters. We have given this equation. used for localization, mapping, model building. Here you can see in the figures deliberative robot control architectures. In a deliberative control architecture, the robot first plans a solution for the task by reasoning about the outcome of its actions and then execute it. You can see the senses, perceptions, then modeling, planning and take exercise, then finally the actuators. Control processes goes through a sequence of sensing, model update and planning steps. Deliberative control architectures. Advantages. Reasons about contingencies, computer solutions to the given task, goal directed strategies, problems. Solutions tend to be fragile in the presence of uncertainty, requires frequent replanning, reacts relatively slowly to changes and unexpected occurrence. Behavior based robot control architectures. In a behavior based control architecture, the robot's actions are determined by the set of parallel reactive behaviors which map sensory input and state to actions. Here you can see the reasons about behavior of the object, plan changes to the word, identify object, monitor changes, build maps, explore, wander and avoid objects, sensor and actuators. Behavior based robot control architectures. Reactive. Behavior based control combines relatively simple behaviors, each of which achieves a particular subtask to achieve the overall task. Robot can react fast to changes. System does not depend on a complete knowledge of the environment. Emergent behavior resulting from combining initial behaviors can make it difficult to predict exact behavior. Difficult to assure that the overall task is achieved. Complex behavior from simple elements, Braitenberg vehicles. Complex behavior can be achieved using very simple control mechanism. Braitenberg vehicle, differential drive mobile robots with 2 light sensors. Complex external behavior does not necessarily require a complex reasoning mechanism. Here you can see the two lights, how the coward is taking place. Aggressive and now the simply how it understand this what is going to be there, its love and explore. So, it will understand the different mobile robot with two light sensors. Behavior based architecture, subsumption example. Subsumption architecture is one of the earliest behavior based architecture. Behaviors are arranged in instinct priority order where higher priorities behaviors subsume lower priorities one as long as they are not inhabited. Here you can see the sensors and the actuators. Subsumption example. A variety of tasks can be robustly performed from a small number of behavioral elements. You can see a robot which has been defined. Reactive behavior based control architecture. Advantages: react fast to changes, does not rely on accurate models. The word is its own best model. No need for replanning. Problems: difficult to anticipate what effect combinations of behaviors will have. Difficult to construct strategies that will achieve complex novel tasks. Requires redesign of control system for new tasks. Hybrid control architecture. Hybrid architectures combine reactive control with abstract task planning. Abstract task layer, deliberative decisions, plans goal directed policies, reactive behavior layer, provides reactive actions, handles sensors and actuators. You can see here the abstract task planning, behavior activations, pre-processed sensor data and behavioral set, then it goes to motors and sensors. Hybrid control policies, the task plan and the behavioral strategy. Example task: changing a light bulb. You can see when a robot changing a bulb, what are the activities are going to be taking place, how it will remove from that place and easily it will place the bulb, sensing each and every activity. Hybrid control architecture. Advantages: permits goal based strategies, ensures fast reactions to expected changes, reduces complexity of planning. Problems: choice of behaviors limits range of possible tasks. Behavior interactions have to be well modeled to be able to form the plans. Traditional human robot interface, teleoperation, remote teleoperation, direct operation of the robot by the user. User uses a 3D joystick or an exoskeleton to drive the robot. Simple to install, removes user from dangerous areas. Problems: require insight into the mechanism, can be exhaustive, easily leads to operation errors. Human robot interaction in intelligent environment. Personal service robot, controlled and used by untrained users. Intuitive, easy to use interface. Interface has to filter user input, eliminate dangerous instructions, find closest possible action, receive only intermittent command. Robot requires autonomous capabilities. User commands can be at various levels of complexity. Control system merges instructions and autonomous operation. Interact with a variety of humans. Humans have to feel comfortable around robots. Robots have to communicate intentions in a natural way. Example, Minerva, the tour guide robot. See me Bonn. This is Minerva experience. Intuitive robot interfaces, command input, graphical programming interface, user construct policies from elemental block problems. Problems: required substantial understanding of the robot. Joystick pointing interface. Humans point at desired target in the world or target specification on a computer screen. Problems: how to interpret human gesture, voice recognition. Humans instruct the robot verbally. Problems: speech recognition is very difficult. Robot actions corresponding to words has to be defined. Intuitive robot interfaces, robot human interaction. Robot has to be able to communicate its intentions to the human. output has to be easy to understand by humans. Robot has to be able to encode its intention. Interface has to keep humans' attention without annoying her. Robot communication devices. Easy to understand, computer schemes, speech synthesis, robot gesture. Example, the Nursebot project, Nursebot Pearl assisting nursing home residents, Longwood, Auckland, May 2001. Human robot interface, existing technologies, simple voice recognition and speech synthesis, gesture recognition systems, on screen text based interaction, research challenges. How to convey robots' intentions, how to infer use intent from visual observations, how can a robot imitate a human, how to keep the attention of a human on the robot, how to integrate human input with autonomous operation, integration of commands and autonomous operation. Adjustable autonomy. The robot can operate at varying level of autonomy. Operational model, autonomous operation, user operation, teleoperation, behavioral programming, following user instructions, imitations, type of user commands, continuous, low level of instructions, that is teleoperations, goal specifications, task demonstrations. Here you can see how a user is having this robot agent is there, where in the side abstract state, learning components, commands are being there, dates and MDP interfaces, activation event, behavioral element, and then actions and perceives environment. Social robot interactions. To make robot acceptable to average users, they should appear and behave natural. Additional robot focuses on the user on the task. Attention forms the first step to imitation. Emotional robots. Robot exhibits emotional responses. Robot follows human social norms for behavior, better acceptance by users, users are more forgiving, human machine interaction appears more natural. Robot can influence how the human reacts. You can see the social robot example Kismet. Kismet regulating the interactions, intensifying face stimulus, human, Cythenia, Brachygyl feral, and brain successful. MIT artificial intelligence have developed this thing. Social robot interactions advantages. Robots that took human that show emotions can make interactions more natural. Humans tend to focus more attention on people than on objects. Humans tend to be more forgiving when a mistake is made if it looks human. Robots showing emotions can modify the way in which humans interact with them. Problems. How can robots determine the right emotions? How can emotions be expressed by a robot? Human-robot interfaces for intelligent environment. Robot interfaces have to be easy to use. Robots have to be controlled by untrained users. Robots have to be able to interact not only with their owner but also with other people. Robots' interfaces have to be usable at the human's discretion. Human-robot interaction occurs on an irregular basis. Frequently, the robot has to operate autonomously. Whenever user input is provided, the robot has to react to it. Interfaces have to be designed human-centric. The role of the robot is to make the human's life easier and more comfortable. It is not just a tech toy. Adoption and learning of robots in smart homes. Intelligent environments are not stationary and change frequently. Requires robots to adopt. Adoption to changes in the environment. Learning to address changes in habitat preferences. Robots in intelligent environments can frequently not be pre-programmed. The environment is unknown. The list of tasks that the robot should perform might not be known beforehand. No proliferation of robot in the home. Different users have different preferences. Learning to interpret sensor information. Recognizing objects in the environment is difficult. Sensors provide prohibitively large amount of data. Programming of all required objects is generally not possible. Learning new strategies and tasks. New tasks have to be learned online, in the home. Different inhabitants require new strategies even for existing tasks. Adoption of existing control policies. User preferences can change dynamically. Changes in the environment have to be reflected. Learning approaches for robot system. Supervised learning by teaching. Robots can learn from direct feedback from the user that indicate the correct strategy. The robot learns the exact strategy provided by the user. Learning from demonstration, imitations. Robots learn by observing a human or a robot perform the required task. The robot has to be able to understand what it observes and map it into on its own capabilities. Learning approaches for robot system. Learning by exploration. Robots can learn autonomously by trying different actions and observing their results. The robots learns a strategy that optimizes the reward. Learning sensory patterns. Learning to identify objects. How can a particular object be recognized? Programming recognition strategies is difficult because we do not fully understand how we perform recognition. Learning techniques permits the robot system to form its own recognition strategy. Supervised learning can be used by giving the robot a set of pictures and the corresponding classification. As we have seen just in this picture that a detail of how a chair is being formed, things have been given in different axes and all. Neural networks and decision trees will play an important role in that. Learning task strategies by experimentation. Autonomous robots have to be able to learn new tasks even without input from the user. Learning to perform a task in order to optimize the reward of the robot obtains reinforcement of learning. Reward has to be provided either by the user or by the environment. intermittent user feedback, generic rewards indicating unsafe or inconvenient actions for or occurrences, learning task strategies by experimentation. The robot has to explore its actions to determine what their effects are. Actions change the state of environment. Actions achieve different amounts of reward. During learning, the robot has to maintain a level of safety. You can see the example of reinforcement of learning in a hybrid architecture. Policy acquisition layer, learning task with supervision, abstract plan layer, learning a system model, basic state space comparison, reactive behavior layer, and initial competence and reactivity. Robots are an important component in an intelligent environment. Automated devices provide physical services. Robot systems in these environments need particular capabilities: autonomous control system, simple and natural human robot interface, adaptive and learning capabilities. Robot has to maintain safety during operations. While a number of techniques to address these requirements exist, no functional satisfactory solutions have yet been developed. Only very simple robot for single task in intelligent environment exist. Thank you.
With this note, thank you, sir. Thank you so very much for explaining us in detail about the robots, the architecture of the robot, the types of robot, their history, as well as applications. If we talk about the applications, about the robots more, in future, what could be the usage of these robots?
As we have just discussed, Geetika ji, regarding that different kind of rules which are coming, especially in the homes and all, for a small work also robots are very much already in use. But anywhere as where any kind of automated kind of activity is taking place, robots can be used. Only important thing, as we have just discussed, the architectural design and the behavioral sensors and all need to be developed in a much more good way. As we have mentioned, because a good sensor is required in a robot to provide a better information. How this he can access it easily, and based on the robot, based on those kind of activity, robot can easily understand and demonstrate the actions he has to take place, the programming he has to expect. So there are a lot of development need to be done in the area of this robotics. Lot of robots are already working, as we have just mentioned, especially in the area of machine learning. The robots are very much in use in the area of providing training to the trainers. Robots are very much in use. Robots are being used as a trainer to provide training to the robots. So by machine learning, and lot of operations need to be developed, and still lot of work is going on. So the robots are almost going to be used everywhere where automation kind of activities are being taken place at the moment. Now, as we have just discussed, that emotions and other things need to be stored into the mind of these robots, so that easily they can interact with a human or the other human faces who are not directly interacting with the robots. Just like the example we have given, the person, if you are an owner of a robot, maybe that robot understand you well, but what will happen if the other human being is going to be interacting with them? So this kind of some of the problems which is going to be faced by this in the robotics area, because the moment you go beyond a certain technology, this becomes a very costly affair. You know, a lot of robots are being used now as a security guard, or for a small activity, for cleaning activity, for different kind of home activities. But those robots are cheaper compared to that if you are going for a good quality of robots.
This was the question regarding the applications, and you very well versed out how the robots can be used in near future. But again the question arises, though it could be very complicated, could the intelligence of a human or the intelligence of the robots can be matched together, or there is any comparison between them?
No, as we have just discussed something about in this lecture also, technically there is no comparison, but humans are trying to store their mind to deliver something through the robotic system. As the objective is that to the mind, the rules of the minds can be stored into the robot's activity, so that it can perform well, it can sense well, it can behave properly. So many things need to be done, but it is not that much easy, as because human mind have a different kind of capabilities, which it is not very easy to fit into the system in the robot. But still a lot of research is going on, and definitely a lot in different area these robots are going to be used. As already you know, in the area of medical, in the area of education, in the different industrial area, their robots are very much in use, and lot of research to do much more development is going on.
With this note, thank you sir, thank you so very much for delivering such a nice lecture, a very interesting lecture. I hope that all the students who might have watched us right now would find it interesting, and I would like to tell you all, in near future we would be conducting series of lectures on robotics, so that if you have any curiosity inside you, of course that curiosity would be helpful, or that curiosity would be fulfilled with the help of these lectures. Thank you sir, thank you so very much.